Todd, how about you take us away here?
Thanks, Lon. Thanks for having me here today. My name is Todd Steele. I'm a former, actually, employee of AWS hyperscaler and spent the last 4 years, close to 5, building the servers in a CM channel. And so we did them with speed internally. And it goes right to your question, Alon, of how I think KPIs are changing actually by the design change that's occurring right now, which is AI. And that's driving a massive change for hyperscalers like Amazon and Google, who have been operating with these outdated operational strategies and philosophies. I lived it myself. And I think to give you some examples, they've been operating off of high-yielding servers. And when I say high-yielding, I'm saying consistently 60, 70 plus on an MPI that rolls out and then gets into production in the 80s, 87, sometimes hitting the 90. And they've just rested on their laurels with that. And what's changing with AI now is the chips. We're moving from a monolithic chipset to these chiplets, and now the yields are really taking a hit as a result, and they can't mass produce these servers out the way they've been doing. They've got to stop. They've got to focus on the yields. The other thing they've been working on is supply chain, and supply chain in particular has been all about KPIs of capacity is the number one. Build it, fill it, run it, get your servers up and running and get your data flowing. And so it's been really a commodity in a supply chain of getting as many parts as you possibly can, securing those and getting the speed of which you're building those servers into the data centers up and running. And when you're moving into the AI space, that's breaking. The manufacturing capacity is not there for these new server types, i.e. liquid cooling is driving that. And so it's a reactionary phase that the hyperscalers are going through right now. That's another one that they're actually caught a lot of them off guard, and that's how do you deal with liquid cooling or cooling of these new AI machines and it's all reactionary, and it's really a race to figure out how to deal with these versus that design, to your question, the KPI driving that design in that manufacturing for design, manufacturability, able to build that in and be able to run those in the data center without having to figure out how to come up with a cooling capacity for these boxes. The other thing is raw capacity. They've just, again, been filling these data centers with capacity as quickly as they possibly can with lower unit servers, lower 1U and lower cost servers. So they've just been able to pump them in and hold lots of inventory and get those data centers full. And then, as I mentioned before, moving away from the monolithic chips to the chiplets now and having to stop and really focus on what that is driving from a yield perspective. And when those yields are so much lower, sub 20% in a lot of cases we saw on the initial ones that were coming out and still are in that range, that throws your whole supply chain and your whole model, your whole business model into a loop.
And hopefully today on this panel we can talk a little bit about the solutions that you found and the recommendations that you have for folks. We'll definitely get back to you. I'd like to continue the conversation with JP here. When we talk about frontier designs, I'd say Cerebras has one of the most wild designs I've seen. I'd love to hear a little bit about, how this wafer scale engine that you've built over the years, which promises great gains, right? I mean, bandwidth, latency, scale, et cetera. It also brings challenges, right? A lot of challenges in manufacturing and deploying, a lot of technical hurdles. And I'd love to hear a little bit about the bottlenecks and challenges that you've run into and how you guys have been addressing it. And please start with your own introduction, JP. Thank you.
Thank you. Yeah, so my name is JP Fricker. I'm Chief System Architect at Cerebras and also a co-founder. So as you heard, making chiplets on a chip is a little bit difficult. Some large companies have tried, are still trying, are getting so-so results. 10 years ago, we saw that, and we saw also the opportunity to provide us another solution for the AI market that was growing. And when we saw that we needed to make a big chip, very large. And we thought at first to reassemble it with chiplets. But the technology was not mature at the time, especially for the bandwidth that we needed across those chiplets. And so we went monolithic. That is, we actually create a single chip that is the size of a dinner plate. It's a 300 millimeter wafer, and the chip is about this size. One chip, 20 kilowatts on it. And so many challenges to power and cool, and also to package it, because no one could at first make it, and no one could package it. And not put it in a system to power and cool it. So we had to look at that holistically, and by tackling the problem very differently than what the industry has been done for years, we thought that doing monolithic and taking into account the defects from the get-go at the architecture level, we could actually mitigate this problem of yield. This is what we did. We simplified the cores within the design. We made those cores very small. Also simpler to design, very small. We associated memory with those core, so very tiny. And then we put 1 million of those on the wafer, 1,000 by 1,000, to create about 1 million cores on one chip. By doing that, we were able to identify where there were defects on the wafer. For every wafer, the defects map is different, and map those out such that the wafer is exposed to the upper layers of software as a uniform, pristine solution. So by doing that at the architecture level, we were able to compensate for defects, not only in manufacturing the chip, but also in packaging the chip, in packaging it into a chassis, in power delivery, in everything. So in every element of the scale-up solution, from a chip all the way to the data center, we include features and processes to work around defects to mitigate this yield. So we don't target 100% yield at every step. That would be unbearable and way too expensive and impractical. But to actually be more agile and speed things up, we do it such that the overall yield is actually close to 100%. And we do that by working around the defect that we tolerate in the design at every level. To cool and power this thing, we had to invent new ways to do it. People in the industry that were used to do cooling for chips, they were unable to do that for this large chip. We had to do that ourselves. Manufacturing the cold plate, we had to do that ourselves because no one could actually use the techniques used traditionally to make those cold plates. To actually install the cold plates, we had to look at CMs that were able to deal with water in ways that was not for a tiny cold plate, but for very big pipes, like 2 inches pipe, getting to a chip is something that we're not used to. And then that's a lot of water cooling, but you also need the power. So the CMs were not able to actually implement the infrastructure needed to test the entire system at the end. So you needed to build a mini data center at the CM just to do the burn-in test and final test that sometimes can last a couple of days or a couple of weeks, depending on what you're trying to solve. So that is a very big shift from traditional infrastructures at the CM, but it's also full of opportunities. So this is where you can innovate, outperform, and outgrow what was there in the first place. So these opportunities are great because it allows new fields to be developed, new method, new tool, and take advantage of the innovation that's happening now. And so we grew from making prototypes in a small lab in Los Altos to now producing at scale, and we deploy in data centers by the hundreds at a time. And the limiting factor is not making, is actually powering. Our limit today is to find the power, to find the right place for the right power at the right cost, and that's very difficult to do these days because everyone is stranded in power. So we go deploy in old equipment or industrial environment where we can get the power and deploy very rapidly. And it's not in actually manufacturing the parts, interestingly.
Thank you, JP. By the way, what is just give us a sense of the benchmark with this approach. How do you describe the performance that you get out of these servers that you've been building?
Yeah, thank you for asking that. I tend to be over speaking about my own field, and then I forget about the company intent in the first place. We can actually outperform any inference offering by at least 10 to 20x anyone else. Even other startups that are doing a similar approach like ours by using SRAM very close to our processors are not able to get the benefit of the bandwidth, low latency and bandwidth on the chip itself. Even across multiple chips in a data center where you have hundreds of those chips together, we have a method and a solution that allows us to outperform those solutions. So it's 20x faster than a GPU solution. Yes, it's harder to make, but you also need about 50 times less silicon to do the same thing. So you do it in a way that's not partitioned in many systems. You do it in one system, so you can throw at it a little more cooling cost for the cooling infrastructure, a little more cost for the power infrastructure. But when you normalize per performance, we're cheaper, faster, and better.
Thank you for sharing that. So this is our version of co-opetition here, because we're about to talk. I'm actually not familiar so much with the details, right? We're all focused on manufacturing, but we've got Alvin Clark here, whose company has brought on another frontier design, taking a little bit of a different approach. He's going to talk a little bit about, Blackwell, which has really changed, has really brought a new paradigm of really also cooperation, I think, in the industry with the MGX ecosystem. So I'd love to hear a little bit about that. That's also introduced water cooling. Everyone's freaking out about power also as a result. I mean, obviously, tokens per kilowatt is very, very important, but we need a lot of kilowatts because we have demand for a lot more tokens. And Alvin's also part of Metropolis. And Metropolis is really helping the manufacturing ecosystem by bringing AI solutions to it, right? And so it's really interesting to see a company that's doing a lot of their own manufacturing, but also developing their own tools that they're offering to the broader ecosystem. So Alvin, if you could introduce yourself and what is this MGX ecosystem? What is Metropolis? What are you guys trying to achieve? It'd be great to hear a little bit about that.
Yeah, thank you, and thank you for allowing me to participate in the event. My name's Alvin Clark. I'm part of the developer relations team at NVIDIA. So I work with the manufacturing and the industrial ecosystem with companies like Instrumental, helping to adopt AI and our technology to bring innovation to manufacturing and industrial opportunities. So Alan mentioned some Blackwell coming up from Hopper, and there's really kind of taking a step back a little bit. There's hopefully two things that we can all agree on. One, Moore's law is dead, right? The idea that transistors are just going to cost less and less and go faster and faster in the pace that it was before, it's no longer the case. The other one, even before you start looking at AI workloads, there is a significant shift from general computing to accelerated computing. So all the existing infrastructure that's out there is moving away from traditional CPU-based compute to GPU-based compute, and that's before we even start talking about next generation workloads with AI. Talking about just the existing workloads that were being there with GPU. So you have these two big exponential kind of activations that are really changing the data center. And so Blackwell, if you look at a comparison to Hopper, it's a great example of what we call extreme co-design, right? Because there is now limitations on just how much faster you can turn the clock frequency on a chip, it means you have to innovate within the chip, outside the chip, in the power system, in the rack, in the network. You have to be on the software stack in order to get these 10x, 30x performance gains from generation to generation on a yearly cadence, right? As we have now with Blackwell and now Rubin coming up and so forth. And you start looking at different workloads. So from a manufacturing perspective, this means that there is significant going to change. It is no longer just making a new chip and that's going to go into essentially the more or less the same server that the previous generation came in with maybe a little bit faster memory. You're talking about now at a very fast pace, every aspect of the data center, from the power design, the cooling design, the way the racks works, the networking, will change at a particular pace. At the same time, not only are we replacing the existing infrastructure, we are now having to add additional infrastructure because of all the great things and the workloads that AI is trying to be. So kind of what our role is in the way we try to foster the ecosystem is just like how we use our own AI tools to design Blackwell, to design Hopper, to design Rubin that's coming out. We're helping the companies that are now innovating within manufacturing so that they can use AI tools the same way we're using to design the infrastructure. They can use AI tools to innovate on the manufacturing front, because we're a long way away from being able to commoditize AI infrastructure manufacturing.
Thanks, Alvin. So, Todd, you're a real practitioner, many decades in manufacturing. By the way, I also started my career in semiconductor. And when you move from semiconductor to electronics manufacturing, it's kind of shocking, right? The controls aren't there, process controls, obviously the inspection steps, the tools. I'm going to throw you a little bit of a curveball, but you can take this wherever you want. So as someone that's gone from semiconductor, what JP just talked about, I know Alvin talked about a little bit, into electronics, perhaps you can think about some of the best practices that you brought over when it came to server manufacturing, and how are those applicable to these challenges that all three of you have just mentioned, and hopefully that turns into some advice for folks in the audience.
It's good. Thank you for that. It's I did put 23 years into semiconductor prior to going to building servers at AWS, and that was with Motorola and Intel. And at Intel in particular, I went through a 2-year lean transformation at the fab in Colorado Springs, Colorado, that became the 8-inch, the fastest 8-inch silicon factory in the world. And it was, to answer your question, it was precisely around focusing on precision. And so when you focus, and I think the group before us talked about that, and when you start really moving your mindset away from speed can be, precision is speed. When you're precise and you do things accurately, and we kicked off our training from NASCAR and pit crew NASCAR training. I took my technicians from the equipment technicians at Intel and ran them through a NASCAR course in our cafeteria. I brought a car and put it in the cafeteria because it's to really get in those guys' head. There's the guys that have been doing maintenance for 20 years or more, and they're the ones that are used to being called on their days off because they can rush in and be the hero. And I just laugh, Alvin, when you were talking about me at AWS, how many years later, and this big mass, I'm building 1 and 2U servers, and now I'm building 14, 16, 12U servers, and I'm looking at this thing and trying to use the technology to make it precise with like cameras. And ironically enough, really, it's all about what you're saying that you're doing at NVIDIA, we're doing at AWS. We're trying to layer on AI to produce the AI servers that we're trying to build. Because I've always been a proponent, another answer to your question, so it's precision, but it's also focusing on the inputs. And in this industry, these hyperscalers have been hyper-focused on the results. Fill the data centers, build them, doesn't matter what they yield, build them. And now you're pumping out $275,000 plus servers per GPU, and you're like, wait a minute, I can't take this 20% hit and just keep pumping these things out. There's not enough in the pipeline, because that's another thing is now hyperscalers are focused on capacity, and yield drives capacity. When you take your test capacity and you have to retest, that's your capacity lost right there. So again, it's precision is that speed, but it's the inputs. And when I say inputs, it's using systems like LightGuide I put in place, because LightGuide uses the cameras at each step of the server build process to tell the operator to do it right. But it's just like your Tesla, it's actually collecting data around it the entire time, and it starts to build a database to say, hey, now I can use this AI. I know what either components are going to fail, or I know what operators are going to hit because it's in the server build process. So you start making those pre-advanced changes to the server build process, and lo and behold, the yield flushes out the end. So precision is speed, and that would be my takeaway today too, is precision is speed, and really focus on the inputs, and the outputs will take care of themselves.
So I'd like to let JP respond to that.
Yeah, in our case, I like the shift between worlds: semiconductor, PCB manufacturing, everything in between with the OSAT. We had to make a chip with the fabs vendors, right? TSMC is making our chip. We had to find a way to produce such a large chip with them. On the other extreme, we had to package it in a chassis. In between, there was a no man's land zone where everyone was telling, don't go there, you're going to get a boom, right? You're going to get something that doesn't work. Everyone told us, no, 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 don't do it. And yet we actually recklessly went into this and had to invent a new way to package. With it, there was a lot of innovation in the way we architected the process to do it, so that we could yield. It's not just the architecture of the chip, it's also how you actually put it together. And by this, a lot of environmental condition that you typically use in a fab, super clean, was not present in the packaging we wanted to do, and which was closer to what you do in a typical PCB assembly house. So there is not only finding ways to observe and correct, but there are ways to actually start clean from the get-go. Start clean in places where before you might not have thought about being that clean. PCB becoming manufactured in ways that are super high yield requires some of that. Well, we have to push that towards the package, and we have to push that from the silicon best practices or silicon fab best practices into this clean room that we had to set up ourselves and build it and then propagate it into CMs in a way that they could accept it. Even though they were not fab guys, they were not OSAT either, but they can actually accept it. So there is changes that has to happen to enable this type of industries that are very specific to the demand that this brings to the table. So there is benefit in performance, but that propagates to demands at the factory in the way we do this. And agility there is key, because we cannot spend 2 years trying to figure it out. We have to do it right away in a matter of speed that makes everyone in the industry uncomfortable, because they know typically how to sequence this to get the right yield at 100%. Well, you cannot afford that. You have to cut corners in a way that maintains the overall end yield, but cut corners in some specific areas. That, knowing where to do that, and that wisely so that you can still scale, is the trick. That's the hard part. How can you still scale and maintain that yield?
So that's some good insight. I'd actually want to come back to some of that in a moment. Alvin, maybe you could kind of bounce off of some of what Todd talked about. You're working on new technologies to drive precision, really, in the manufacturing ecosystem. Is that true? Maybe we could hear a little bit about what's coming down the pipe, and what are you excited about, and how are we going to be able to get closer to that precision in order to unlock speed and obviously hit KPIs?
Yeah, 100% appreciate that. Yeah, a lot of the biggest headwinds that we hear about from end manufacturers are around operators, right? That is probably the biggest challenge that we see now. Both, one, you can't throw human capital at manufacturing problems the way you used to. Two, nobody's really gone into manufacturing for a long time. And so we're also facing a brain drain. I've heard a stat, something like the average age of Airbus of workers at Airbus's facilities in France is like 57. So in 5-6 years, there's a lot of that tribal knowledge that is going to leave. And as you all hear today, we're making significantly more complex products: electronics, semiconductor, cooling systems, thermal, and just kind of talking about the data center. So the skill level that is going to be required by these operators, it also then becomes a lot higher. So the innovations I'm really excited about from the companies I work with in my ecosystem are those that are bringing what I call AI superpowers to operators, because we're still a very long way away from a fully lights out factory. So now is, how do we get somebody up to speed? How do we get someone trained? How do we give them the intelligence, right? So they're not getting called on a Saturday because they're the subject matter expert on one particular process or machine, but that knowledge is readily available so that anybody can, through a phone, a tablet, a human-machine interface, is able to ask questions and say, what is going on here? How do I minimize downtime? How do I clear this error? How do I recommission a product? Same thing goes with, we talk about just speed of light, just in the terms of physics, just how fast can I possibly just do a process, right? And a lot of that is, if I can create intelligence, if I can create training material from my design files, that I can already have my operators trained so that I can software define, commission a modular manufacturing facility or station so that it is ready at NPI and it's all ready to go, then of course, I can go and have that speed and that accuracy a lot faster. So it's really these companies that are bringing in this next level of intelligence, support, assistance to the factory floor, to the workers, that I'm super excited about.
So this is actually, and I'm gonna throw one for you two. So both JP and Todd, at the end of the day, who's building the products? It's a manufacturing partner. In fact, I know you've got a manufacturing partner in common, right? And Alvin's talking about bringing them technology. JP, you're talking about pushing their limits. Todd, you're talking about driving precision. I'd like to perhaps hear a perspective of, look, I don't own the shop floor. I do not own the training of the operators, right? I am perhaps a brand that is trying to get something built and I want to deliver compute to my customer, right? So if the technology needs to be deployed at the shop floor and you don't own it, how do you deal with that, right? How do you drive precision from the outside while you're the customer? You don't own everything that's going on in that facility. So how do you get over that? And I'd like to hear, Todd, go ahead.
Sorry, for me, what I was working on is standardization. And again, I brought up the augmented reality tool. It's a specific one I used was Light Guide. So you have, it's similar to what Amazon's doing in the fulfillment centers, pick to light. It's essentially takes your training curve and that knowledge, Alvin, that you're talking about on these individuals that have been there for years, down to, I was literally training operators in minutes or days because they're essentially following augmented reality work instructions. And so that's how you standardize, and then you repeat the exact same task over. And when you standardize and repeat, you get the good, you know what you're going after from a good result. In this case would be yield, because as I talked about before, yield is a capacity hit. And that's what you can't afford in these. So the standardization, driving, and you have to do it carefully, because I brought it up that I did it with the technicians at Intel with NASCAR. You have to find something that they can relate to and say, hey, this thing's not here taking my job. This isn't a robot taking my job. Change is good, transition's tough. You've got to transition the team through that these cameras up here now are to help you. To your point, I can go now on a screen, and when something fails, a AI tool such as Instrumental can tell me, go check this connector, or go plug this in again, or check this battery, because 9 times out of 10, that's what's going to solve it. So that's what's driving it. It's a little bit a long-winded answer, but it's standardization of that precision I talked about that changes that culture.
So, but you're changing the culture of a shop floor you do not own. Those operators are working for your manufacturing partner. And that manufacturing partner may not be incented or may be incented to bring in this technology. So how do you go and you now have a vision for technology and you've got to bring it to your contract manufacturer?
Yeah, in AWS's case, it's pretty easy because they own everything. The contract's owned by AWS, so it's essentially go thou shalt go do. But yes, the thing is, you don't want you want to change that culture that I'm talking about, and it drives down cost by getting these results, and then everybody is essentially making more money.
Aligned on that, yeah.
Yeah.
Incentives, JP?
Yeah, in our case, I see things in two ways. One way is these systems are becoming excessively complex to put together, and therefore the only way to really make it consistently and with a high yield is to think about design for automation. So you're going to have to replace the manual labor with automated labor and use the manual labor available to do the evolution, the dynamic changes that you have to incur on a production line. The repetitive one, leave that to a robot or an AI assisted robot that can improve its own behavior, use humans and their ability to modify and be agile in the way you do it, because from one production line to another, maybe you have a temporary time where you don't have full automation, so you use the people for those, for agility as opposed for repetitivity. I think there is a huge potential there that CM needs to tap into. And how do you get into a production that you don't own? Well, you partner with them. I mean, they're not just like on the other side of a fence. You just go on the floor with them and figure out the way to work together on getting that done. And that includes automation too. I mean, if they need to build something brand new with automation that they have never done before, let's just go do it, because today that automation might be far, far simpler to get and get in place than it was 15 years ago. And so you need to have that agility to go and absorb and adapt to new novelty in terms of how you build a product, in how you use the equipment, and how you use the people to coordinate all this. I think there are plenty of opportunity here. And this AI market with such a demand is the perfect field for this innovation. So it's not just about building products, it's about building the factories that build those products. And there is a ton of opportunity there.
Alvin, it's interesting. You're developing a lot of these technologies internally at NVIDIA. I'm curious to hear your perspective on what are some of the challenges in having the ecosystem adopt these new technologies? How have you thought about overcoming those challenges? And I think the zingers really, how do you operate in a world where you've got brands and you've got CM, JDM, ODM, manufacturers who all need to work together, right? And you're getting different opinions from both sides. So can you share with us?
Maybe it's a little bit about the same co-opetition, I think is what Anna mentioned. But it's really kind of a little bit what JP and Todd mentioned about that it's the high tide that rises all ships, right? It's an ecosystem and a standardization, best practices, the technology that is relevant, that delivers tangible business value. At the end of the day, you want to sell more of your products. It's successful if the manufacturer builds them a lot faster. Quality goes up, margin goes up, right? So any partnerships where you can go and sit down and be like, what is this very difficult problem that is about either building this server, building this power system, whatever it might be, and you can partner and use the technology, bring in partners from that ecosystem, solve that problem, and then being able to communicate that and drive awareness to this new solution, to this methodology, then that is something that the rest of the industry can adopt, can add their own innovation on top of it. I see maybe a little bit like open source software, right? Highest quality, right? Because everybody's putting into the situations. And to one of Todd's comments about changing culture or the people that might say, hey, this is going to take away my job or anything else. One of the things that we actually found out, it was a study that was done, I think it was Harvard or MIT, I can't remember, bringing in co-pilots and operator assistants onto the factory floor. The operators actually felt more empowered. They felt more secure in their positions. And you can kind of see that makes sense. You're no longer, hey, I always got to go ask the subject matter expert every time there's a question. I don't know how to do this. I don't know where to get that intelligence or the ability to do that. But now, because that's just readily from a natural language prompt away from you being able to understand how to work a machine, the process around an assembly, whatever it might be, maintenance, then you're like, hey, I have intelligence. I am empowered. Feel more comfortable in what I have to do. I feel more comfortable in my job. My stress is a lot better. We actually had a partner, and their end customer came and gave us a talk. And the guy goes, well, I want to thank you guys because my plant manager can spend time with his kids, right, on the weekends. Because all this operator training and systems that you guys stood up via the partnership allows him to not have to come in every time there's questions or emergency because that intelligence is readily there. So, and then hopefully that is a momentum that helps to drive cultural change, that less turnover. That's something manufacturers have to deal with, right? So happier workers, happier subject matter expertise, ability to disseminate all your own practical enterprise knowledge to all your new employees and operators is a great deal. So I think you'll see a little bit of momentum as the technology gets adopted, that everybody's going to see the benefits and continue to build upon it via the ecosystem.
I'll just tie on those technicians I talked about, went through the NASCAR training. It was exactly that. It went from a finger pointing, blaming culture to one of, oh my God, I let my teammate down. I did something that they had to find or have to deal with. So yeah, it very much does. Safety incidents went to about 0 and costs go down and the whole culture is better. It's a Toyota production system. It's been around for years, same results.
Todd, I've got to hear though real quick. What does it really mean, NASCAR training? Like you got to paint this picture. Like what does that mean? You walk into a factory and just give us a story real quick.
So it's a real thing, and it's ironically enough, the Navy has been doing it on aircraft carriers for years. It's about everything has a place, everything's in its place, nothing less, nothing more. Because if a jet flies off this thing and has a socket stuck in the engine, and if, however many $1 million jet and potentially kills somebody, that's unacceptable. NASCAR pit crew looks to be hurried. They're actually not hurried one bit. Everything is extremely precise. So think of the cutouts in the toolboxes. Think of the lug nuts already stuck to the wrenches when they pull in there. And it's zzz, and the wheels are so quick because it's precision. The jack is exactly staged. And by the way, they're using a form of AI for years. Cameras, they film every pit stop. And they jump across the wall. And as a team, they go, hey, if I move a 1/8 of an inch this way, I could shave off, half a second.
Wow. Zach, Scott, if you're hearing this, maybe you got to bring this NASCAR training to your NPI programs. I know you talk a lot about speed. Tony as well. I thought that was really interesting. And then for our team, Santiago, we're going to bring I guess they bring like an actual car in because we've got some deployments coming up we need that speed for. Thank you for sharing that, Todd. JP, unless you want to say something, I'm going to ask a wrapping up question. Do you have something to add? You're good. All right. So first of all, thank you all for sharing these perspectives. We did not prepare for this, but I'm going to ask if you could maybe think about if you had a billboard to put up here on this ship, something to tell the whole audience, some wisdom to share. You've all been working on these frontier designs. It's a frontier of complexity. Any kind of lessons you'd want to share? What would be more broadly useful? If you could start with that high level, too long didn't read billboard, if you have it. If you don't, it's fine. I also talk too much. And then share a little bit about what that means and what you've learned from that. You know what, Alvin, how about you start?
Yeah, I think my billboard would be AI superpowers for operators in the factory floor. We're a long way away from lights out manufacturing. Manufacturing is still 85% of, or not more, human in the loop. There is a lot of room for innovation there of how do we give our operators the capability, the skills, the tools that they need. every tool for the right place, as Todd mentioned, and there's a lot of innovation that can be done there to come there. So that would be mine.
Thank you.
So for me, it's more about the experience we had so far at Cerebras and what really matters during that 10 years experience so far. Agility and not taking no for an answer. Every year, for 3 years, we got no, 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 you cannot do it, you cannot do it, you cannot do it. So everyone is going to tell you no. So there is a culture shift that has to happen where you actually embrace something that's really new, that makes you really uncomfortable, and until everyone agrees that that is actually the new way to behave and do this, until then, you're going to feel, so please embrace new things, even though they might be risky. Nowadays, you have to take those risks to remain competitive. So take that as a big plus. Be agile and take risks.
And don't take no for an answer. Todd?
Yeah, I've said it a couple of times, precision is speed, but I really tie it back to the slides that Anna showed, because I really think in this forum, focusing on the inputs and letting the outputs take care of themselves. And I've been dealing with this even at AWS for the past 2 or 3 years, and there's so much energy put into the bone pile and the poor yield and just in getting them fixed and getting them in the data centers versus why did things fail? Stop and ask why. And then with these tools, these slick tools that we have now, the group prior to us, and we've mentioned a few of these cameras, these AI applied to AI, it's incredible how if you drive the inputs, that the outputs will take care of themselves.
Wonderful. Can you get a round of applause for this wonderful panel?